She works. Amazing. Okay, so this is the second lecture. I'm going to move closer to the microphone. Of this series, and I think I've called it matrices, but basically it's linear transforms. So, matrices / linear transforms. And if you don't know what any of those three words mean, don't worry about it. We're going to slowly make our way through them all throughout today. So, just as a very, very quick summary from... I am not a linear transform, I promise. Summary from last time, we were looking at vectors, and vectors were... So, recap from vectors. We had... Vectors were drawn. I normally do an underline for my vectors, but you can also do arrows overhead. So, one-sided arrow, two-sided arrows, or like bold font are all types of ways of notating vectors. When I am in the process of getting the lecture notes from this series up, all of the vectors will be bold fonted rather than underlined or arrow overheaded, because I find that the neatest way, especially when we start having the notation of unit vectors, which, if we remember, were you take the unit vector in the direction of u is u over like that. And if they had arrows, then it would be u arrow hat is u arrow over arrow u. And like, arguably, they're both awful, and the bold font is the nicest one, but this is nicer for me to write. So this will be the notation that we use. But vectors were basically arrays of, or lists of numbers, spoilers. So the vector would be with entries v1, v2, v3, all the way up to some length n, and that is a vector of length n, where all of these numbers then are scalar values. So scalars just being numbers. Vectors have these scalar entries, and what that means is that a vector has size or magnitude and direction. And that's where our third definition comes into play. Ooh, wait, I do a thing here. If I do this, if I just draw a line there. Cool. So vectors have size and direction, and that's where we can draw them as arrows comes in really useful. So and the vector v would be like the vector that takes from the origin to like a point. Call that capital V, and this is the vector v. So from the origin to the point v. And this is where our like ordered, ordered we're gonna spell it that way. Line segment definition comes in. From one point to another point, arrow in between the two. Magnitude, size then being the length of the vector, direction being the rotation. Exactly. We can also then say that vectors have algebra, so vector addition, so v plus w, we do that element-wise, so it's vi plus wi, and you just add each element. So you look in the first entry and you add those together, you look in the second entry and you add those together. And this works really well because it then means that when we introduce these like unit unit basis vectors. So I is 1 in the x direction and 0 in all of the others. And j is 0, 1, 0. Well, 0, 1. Because we're only in 2D, so I don't actually need to do my n-dimensional version of this. That means we can write the vector v as some scaling v1 times I plus some scaling v2 j, which is the same as saying v1, v2. But now this coordinate system way of thinking about vectors is really, really useful, right? Because we're very used to saying our coordinates are x, are the amount we go along our x-axis and the amount we go up our y-axis. And what we mean by that is we are stretching the vector I and we are stretching the vector j, or scaling, or doing a transform to it. Spoilers. Hello, welcome in. We hope you enjoy. Ooh, I'm wondering if I can actually plug in. Can I have more cables on my desk? That is the question. Do you rotate? So I know if the remarkable will go upside down. Not that one. Need more wires. Always more wires. That's what I always say. Doesn't look like it. Okay, never mind. It always annoys me when things plug in from the bottom because it means you can't charge them while they're like using it. Okay, so that's like a very quick road stop summary of vectors, and that's sort of where we got up to. We did also do things like dot products and projections, which will come up a bit later on, but for now, this is how we need to remember our vectors, okay? So today, we're going to be moving on to linear transforms and matrices. So where a vector is like a list of numbers, a matrix is an array of them. So we write matrix A. So matrices I will always denote with capital letters, unbolded capital letters, specifically, unbold. Is given, and we tend to put brackets around it. You can use square brackets or rounded brackets. There is, again, people have preference, and as long as you are consistent within your own notation, you should be fine. I'm going to use squares for most of this. And where in the vector form we had like the list, v1, v2, v3, vn. Now we have two subscripts to denote location. So you can think of it as a11 is the first entry in the first entry of the row, first entry of the column. Second one is a12, all the way up to a1n, similar to our vector. But now we also have column entries as well. So this is the second row in the first column, all the way down to the mth row, first column, and then going across. So this will be a22, and so on, and then eventually you get to mn. So this is an m times n matrix, where you have m is the number of rows, and n is the number of columns. So we, instead of having to like write this all out in this big grid form, what I can also say is just A is Aij. And something I didn't say before, and I think I'm right in saying, is that this, and whenever I do this like subscript notation, is called Einstein notation. And I had a really big stress today trying to remember what this was, because there are a lot of dead men with names that begin with E that we talk about in maths. So I was like, Euclid notation? No, that's not it. Euler notation? No, that's not it. Quick Google, Einstein notation. But what this means is the ith row, jth column entry. So if you think about like Excel spreadsheets, the way that Excel spreadsheets work is they will have like letters along for the different columns and then numbers along the row. And you say like, right, A2 is you go to the eighth column and you go to the second row and you find it that way, which is arguably the wrong way around. This is similar. So our subscripts, the little numbers that I'm writing, just tell us where it is in this matrix. It's kind of like it's finding the stuff in a table, but without the grids. We can definitely turn down the music. So, if I want to do some examples of this, so just some different types of matrices. We have all of these are types of matrices, and the thing that they have in common is they are structured arrays of numbers. Now, I'm not putting commas in between my entries like I would with a vector. And I don't know why we don't. We just don't. Equally, I could write these like this. Again, there is a pro and con reason. I'm sure that someone will have an opinion. But to my knowledge, it's never done me wrong to just not bother to think about which type of brackets I'm using, as long as I am consistent throughout my own notation. I think normally when I'm writing for myself, if it's like PhD research work, I will use these. And if it's A-level work, I will use those. I don't know why. Commas get confused with subscripts if you write out elements with subscripts. Yeah, that's true. Oh yeah, because A1, comma, A, yeah. What about a curly brace? No. Unfortunately not. We don't fuck with that. Okay, so if I was going to describe what type of matrices these were, remember it's M times N, where this is your rows and this is your columns. So the first matrix is 1 row, 2 columns. So this is a 1 times 2 matrix. This is 3 rows, 1 column. So it's a 3 by 1 matrix. And we say by instead of times sometimes. This is a 2 by 2. And this is a 3 by 3. If I was going to denote this, sometimes I do, sometimes I don't in vector form. But I would say a M times N I've seen done, where you do the little subscript of the big matrix is the total number. Aij for I is 1 through N. M J is 1 all the way up to N. So that would be like the proper way to write out all the possible information you could have about the matrix without actually putting in the values. One other thing to note is the 1 by 2 and the 3 by 1. This is what's called a row vector. And then perhaps unsurprisingly, the next one is called a column vector. The other two matrices that we have, when M is equal to N, so they're 2 by 2 or 3 by 3, these are what's called square matrices. Because they have the same number of rows as the number of columns. They don't have to be. M doesn't have to be equal to N or 1. We can have like a 3 by 2 or a 7 by 6. Anything bigger than what I have written out is really tedious to do algebra with. So for these lectures, probably, and I'm not going to say this exclusively because like there might be need to just to show that we can, but for most of this we're going to be sticking m and n less than or equal to 3, just to make the algebra like a bit faster. So that is what a matrix is. I've told you that we're going to be talking about linear transforms. I'm going to do a bit more setting up some definitions from there. But generally speaking, a matrix A is an m by n array of values where all of the scalars entries, all the entries are scalar. Typically they are all, at the very least we're going to be looking at real numbers. M and n do have to be whole positive numbers. Yeah, let's learn how to play with these. So we're now going to set up the sort of matrix toolbox. So 2.1. So we did vector algebra, now we're going to do matrix algebra, and then all of this comes under the umbrella of linear algebra. So first things first, it's easiest to start with addition. So when we add matrices, they must be the same size. And then it's really simple, we just add them element-wise. So we can add two matrices of the same size. So say A, m by n, and B, m by n. Element-wise. So element-wise means, so each one of those like aij's that I was writing, or in vector form ai's, those are the elements of the vectors, or the matrices. So A plus B is just aij plus bij. Okay, so if I was going to write that out in full, I would have A plus B is A11 plus B11 in the first entry, and then this is why like matrices, as I say, it's going to get really big really fast because I'm not doing any delineation. So that carries on until you get A, so first row, nth entry, B1n. That carries on down, and then we have so mth row, final row, first column, final row, first column. The dots just mean like continue the trend. And the same along the diagonal, so all of this is the same. So the final entry, like that. Hi, just got in. Did we figure out that thing about the cosine formula for dot product? Yeah, it was apply it to the arbitrary bases. I don't have it written out, but as soon as we finish the stream, someone posted in it saying, if we get time at the end or like after a break, I will find it and then we'll go over it. Will this be stored for future use? Yes, so all of the VODs will be on YouTube, and I am hopefully I'm in the process of typing up all of the notes for this. Okay, so let's do an example. Let's say A is 2, 0, 1, 3, and B is minus 1, 1, 0, 1. Then A plus B is the matrix. So first entry is first entry and first entry, so 2 add the minus 1. Second, same place, so 0 add 1, 1 add 0, and then 3 add 1. So that's 1, 1, 1, 4. And then that's the matrix. So it sort of makes sense from this definition that you need the same number of i's and j's. If these were different sizes, you wouldn't be able to add them, and you can't just like skip them off the end, okay? If B was actually the matrix, like this, I can't just say, oh, well, this is also 0, 1 here, because you can't add nothing, okay? You can add 0, but you can't add nothing. So they must be the same size if we're going to do matrix addition. Hot take, nonlinear differential equations are cooler. I agree. Nonlinear equations are used for string theory. So nonlinear everything. So linear and nonlinear, we'll get on to actually what that means in a second. Linear algebra is very useful. Equations, differential equations are a different sort of area of maths. And then the linearity and non-linearity of those is different to the linear or non-linear algebra that we're doing now. A lot of maths does rely on a good understanding of linear algebra. And actually a lot of non-linear systems are solved by what's called linearizing. So taking the like linear equivalent of a system and finding a solution for that, and then seeing how it changes when you make it nonlinear, which is really cool. Even like high-level mathematicians are still using like stuff that people learn in their undergrad. I don't know what you mean by that. I'm sorry, friend. Okay, so going on to our second operation. Operation. So with matrices, there's this thing called the transpose. So the transpose of a matrix A is written A with a little t, superscript t, and is given. So if the entries of A are A, I, J, actually let's do this properly. So A is an m by n matrix with entries A, I, J. Okay, so it says m number of rows and n number of columns, and the entries are I and J. Then A transpose is an n times m matrix where the entries are A, J, I. Okay, and what that means is essentially we sort of flip it along its diagonal. So flip the matrix along the diagonal. And the diagonal here, diagonal, are the things A, I, J, where I is equal to J. So the 1, 1, 2, 2, 3, 3, 4, 4 column entries. The leading diagonal, apologies, or main diagonal. So what I mean by that is the AIJs where I equals J. And we'll do an example of that. So let's take A is a 3 by 2 matrix. So 3 rows, let's go 1, 3, 2, 7, 3, 0. Actually, let's go 5, 0, just so that all of our entries are distinct. Then A transpose is, so because we're flipping along the diagonal, I'm going to do really weird brackets for a second. Our main diagonal here are the entries where it's A11, B12, which is these here. Now, it's a 2 by 3 matrix. Sorry, let me just... There. It's a 2 by 3 matrix, or 3 by 2 matrix, sorry. So they don't change. It doesn't go all the way down to the corner. It's not a nice 3 by 3. It's not a square matrix. But what that means is we should have unchanged here. So 1, 1 stays the same, and 2, 2 stays the same. But now this 3 was our first row, second column. So now it becomes our first column, second row. Same with the other one. That gets flipped. And now the bottom 2, that's our first column, third row. So it becomes our third column, first row. Basically, it goes over here. I was like, maybe I can say this in a way that is nice, but it's like, let's just draw it out. It's always easier to just draw it. There we go. Ta-da! So transposing a matrix will be really useful, and this is where I was saying like a column vector and a row vector are basically the same thing, but don't tell anyone. If you are only working with one specific type of vector, because for a vector, is the corresponding column vector. Okay, so V is 2, 3, 7. VT is then 2, 3, 7. Because the only entry, if I was going to do this as m times n, the only one where I is equal to j is that first entry. So it does matter because of how we're doing our, and I did a bad thing and I need to underline my vectors, shame on me. It does matter when we start doing more complicated equations, because knowing if something is itself or the transpose is quite useful. But I could equally write like a vector W as a column and its transpose is 1, 0. It's not to say that all vectors are row vectors and all vector transposes are columns. It's just whatever you define. And this is where like really being clear with your notation is important. Okay. Two more operations. One's nice, one's awful. When we did vector algebra, we did vector addition, and then we did vector scalar or scalar vector multiplication. We're going to do the same thing here, because vector-vector multiplication was really complicated and we had to introduce this scalar product, and there are actually 3 more products under a trench coat in the corner that I'm like, please ignore for the minute, because we don't need them. But we're going to do a similar thing with matrices. It's useful for us to know how we multiply through by a scalar and what that means. And then there we will do matrix multiplication, and that is what it's called. A matrix is a special kind of vector. A vector is a special kind of matrix. So if you think of like, okay, it's going to get confusing because there is like a 2D vector which has 2 entries, it's the number of entries, but if a vector is like a list, a matrix is an array, and there's also like a 3D version or like a bigger one again called a tensor, and then you start getting really weird, but they're all subsets of each other. So it's like vectors are in this space, and then matrices like if this was a Venn diagram, it's like everything inside of all of 3 circles is a tensor, but they're just very, very specific types of each of the other thing. Okay, so scalar matrix multiplication, yeah. I swear these streams, my spelling is the hardest thing. Matrices and vectors are just tuples of numbers, so instead say the same thing depending on n or m by n. So this is where like my tuple feels like a very computer science word. Ordered sequence of elements used in fields like mathematics or computer sciences. So my understanding of that is that a matrix, or like the way you define a matrix, is a vector of vectors. So like if the vector, or like an ordered list 1, 3, 2, 7, then A would be like V W is like, this is sort of how you store them in computer science, which is equivalent to the 1, 3, 2, 7 thing. Vector of covectors. There we go. That's a way to think about it. That's not a helpful way to think about it until the end of this lecture. So for now, disregard that. There will be a point at the end of the stream where I'm like, and we can sort of think of it like this. And y'all will go, aha, that's the thing that Kat was talking about earlier. But don't worry. Hi, Banana, welcome in. Okay, so scalar matrix multiplication is essentially like with scalar vector multiplication, where you distribute that scalar over all of your entries of the vector. We do the same thing. So for matrix A and scalar K, Ka, I really want to write T on this. I'm like, anyway, is Kij. Okay, so Ka11, Ka1n, Kam1, Kamn. So we just, every entry gets its own scaled. Every time you say K, I look up. I'm so sorry. Hey, Cap. Disregard that describes most master. It's so, I have so much like respect for, thank you for the follow, welcome. I have so much respect for teachers, because like I was also one of these people that used to like complain like, why are you teaching me the same thing again but changing the rules? You said differentiation was this and now it's this. And like actually it's so hard writing lecture notes. Yeah, it really do be. Okay, let's do an example. The will is more nuanced became my mantra to students. Yeah, it's life really do be like that sometimes. Okay, so example, so let's take matrices A as 2, 1, 0, -1, and B as 1, 3, 4, 1, 3, 4. I'm just gonna repeat it. Then 3A is every element we're just gonna multiply by 3. So 6, 3, 0, -3. And we can also multiply by negative numbers, and that's the same as multiplying by -1 and then multiplying by 2. Same thing. So -2b is -2, -6, -8. And I define my matrix quite nicely. Like that. So yeah, multiplying by a scalar is scaling every element by the same amount. If we want to scale every element by a different amount, we have to do something way more complicated. And we're not doing that, so don't ask. Okay, final operation. It's the final countdown, but worse. I feel really like I need to move my microphone because I look this way. Like the corner of my two monitors is here. And I'm like, maybe this monitor should be here, and then I'd look that way, but I don't like looking that way, so I like looking this way. I'll make Cap help me when he comes to visit. Okay, so final operation. We want, for now, there are a load more operations. I can get really complicated. I could just define a function that takes any matrix and sets every value to sine of the angle that the sun is in the sky right now. I'm not going to, but I could. You couldn't stop me. Matrix exponentials. Why do you hate me? We don't need it. Do I even remember how to do that? Oh wait, no I do. You just multiply the matrix by itself. We'll get there. Okay. Just made G-force go crazy. Okay. Is matrix multiplication. And then I don't have to remember how to spell multiplication again for the rest of the stream. So it's not the same as matrix addition, where the matrices have to be exactly the same size, but there is a requirement on them. We can only do if the columns, I have to think really hard about this now, columns of the first matrix is the same. Sorry, the number of columns of the first matrix is the same as the number of rows of the second. i.e., for matrix A is m by k, and B is k by n. Good. If A was k by m and B was s by v, bad unless m equals s. Okay, so it has to be the columns of the first matching the rows of the second. Clock that this means that A times B is not equals to B times A. In fact, no guarantee B times A exists. Okay, so not only is it not commutative, like nearly every other operation that we've looked at so far, but it actually can be just ill-defined. It's just not defined, doesn't exist, stop asking, move on. So what is it? So for two matrices, so let's say we can do it, so we do m by k times by a matrix B k by n, will give you the matrix C, which is m by n. So the product of a matrix operation, matrix multiplication, is the same number of rows as the first and the same number of columns as the second. And that should be easy to remember because we always say rows by columns. So it's just the first of the first and the last of the last. But yeah, it's that. And this is then equal to, so the entries are, so each individual entry is the sum over the products. So for T is 1 through K, A, I, T, B, T, J, where I is 1 through M and J is 1 through N. And I think that's right. And I'm hoping a mathematician in chat will check my notation because it always terrifies me when I write that down. It is the dot product of the ith row from A and the jth column from B. Yeah! Fab. That's gross, let's do an example. It's one of those things where like Einstein notation is fab if very familiar with, and is an absolute nightmare and a bit scary if you're not. So let's do an example. So we have the matrix A as 1, 2, 1, 0, minus 1, 3. And this is a 2 by 3 matrix, which means that we need a 3 by something. Doesn't matter what it is, but we need a 3 by something. And I'm going to do a 3 by 3. So 0, 1, 3, 1, 2, 0, minus 1, 5, because I like doing complicated numbers for some reason, 2. So these are our two matrices, and what that means is we should get C as a 2 by 3 matrix. If we don't get a 2 by 3 matrix, we done fucked up, is a good way to check. And there's an interesting property of like, oh, cat, that's the same as the size of A, and it's like, yes, but that's exclusively because B is a square matrix, and we'll get onto some definitions about why that is later. I hope you describe it this way to your students. You lot are my students. There's a reason I don't teach anymore. It's because informal teaching is the best way. We're just all vibing. Okay, so let's do this. I'm going to get myself a nice big bit of space for this. And I'm going to write it out again. So if I write it out properly, 0, minus 1, 3. This is one of those ones where, like, if y'all were sitting in exams, it would be like, always make sure that you copy out the questions properly, because otherwise you're going to make yourself confused. And when you're doing matrices, make sure you write in nice, neat grids. And this is where having a blank background is really gonna screw with me. So, equals 2. Why am I writing in white? Here we go. Equals 2. That should be enough space. I'm going to say that way too confidently, and we'll regret it later. So, we said that the ijth entry is the sum over the products of the itth entries and the tjth entries. And what that means is we fix, so for 1, 1, we fix I and we fix j. So, for this first entry, oh god, this is where I'm using, like, we're going to look at the first row of A and the first column of B. Okay, for the second entry, we're going to look at the, so this is now the 1, I is 1, j is 2. Yeah, I've definitely not given myself enough space here. It's going to be the first row of A and the second column. And then quickly move the brackets and pretend you saw nothing. The third entry here will be, again, first row, now third column. And then we repeat the exact same thing, but with the second row and the first column, second column, third column. And I get rid of all of my colours so I can actually do that. So C11 is going to be given as this multiplied by this. And then this is actually just the dot product. As Innerklein said, I'm doing so great. But we just move forward through t's, okay? So when t is 1, we look at the first entry times the first entry of our row in our column, and then we go add second entries, so 2 times 1, add third entries, 1 times minus 1. I definitely don't have enough colours to actually do this, but we'll do the same thing again. So it's 1 times 1, add 2 times 2, add 1 times 5. You don't have to circle it every time as well. One times 3, add 2 times 0, add 1 times 2. Okay, so just moving down. I'll tell you for a fact I'm not going to need that much space there. There we go. Oh, running out of colours. Okay, so now second row. So we say A2. And we look at this, but then it's still the first entry on the first row of B. So we repeat. So we get 0 times 0, add -1 times 1, add 3 times -1. Okay, and the thing that you should clock here is that as we move this way through our entries, the first bit of each of those multiplications are the same. So it's 1 times something, add 2 times something, add 1 times something on each of the rows. And then here, the things that are the same should be the second entries. And if they're not, you're done fucked up. So they should match, they should match, and they should match. And it'll be the same throughout each of the rows now. So let me just do this. And then, so we've got 0 times 1, add -1 times 2, add 3 times 5. 0 times 3, add -1 times 0, 2 even. No, 0. Add 3 times 2. And that nearly all fitted. It's one of those things that is like, once a lot of practice, it should be alright. But we should have these matching. Oh, you can tell where I lost some space. They matching. That matching. That matching. And that matching. And then the first entries should match along here. So 0 times something, add -1 times something, add 3 times something. Assuming that that is all good, we then just solve that, and that should give us 1, 10, 5, -4, 13, 6, which is in fact a 2 by 3 matrix. Ta-da! Oh, so that's matrix multiplication. And that works for nearly any m by n, or it works for any m by n times n by something else. So as long as the first row, first matrices columns match the second matrices number of rows, it's all good. Ugh. Okay. So far we've been alluding to the fact that matrices and linear transforms have something in common. So we've been alluding to matrices as linear transforms. And now I think we actually have all of the tools to do it. So let's new page this. Consider the vector v with entries vi. Then we can draw this vector as I did at the start, as an arrow from the origin to a point in space. Okay, And we can say again that it can be written as the coefficients multiplied by our basis vectors, our I by j. v1 times I and v2 times j. We can say it as v1, v2, v1, 1, 0, v2, 0, 1. All the same ways of saying the same thing. That it's this linear combination of scaled coefficients, which mean we go along the x-axis some amount v1, and we go up the j-axis, the y-axis some amount v2. If I wanted to map this vector v to a new vector, call it v prime, if I could spell, transform into a new vector, call it v dash, v prime, we can apply a transform. Sort of like a function, but basically that v dash is some map v. So we apply some function, we put some effect on it, and we put in v and we get out v prime. And we can also write this as v sort of maps to through L to v prime. Where this is our sort of transform operator. And what this is just curly script L. I'm just doing capital L for reasons that are we're only going to look at linear transforms, and doing linear transforms as a curly L is really fun. But we could use any notation for this. We could go back to using function notation, but given that we have scalars as lowercase letters, matrices as uppercase letters, and vectors as underlined letters, we're sort of running out of our normal letters, so I'm just going to use this curly L for now. Then essentially what that sort of does is it takes our vector v and sort of moves it in the plane to some new, so if this is v, let's say v prime is actually down here, and I'm going to make that v prime. The map L sort of translates from one to the other. And this is where we're going to shift over to Desmos. And if I can get overleaf to work, we should have, ta-da! Okay, so here we have our I and our j matrix, and what the transform is going to do is if I apply a transformation, I apply a linear map, I can sort of shift things to a new position. And when we apply this map, we don't just apply it to one vector in the space, we actually apply it to like all vectors in the space. So let's bring this back to normal, and we're going to put a vector, say 2, 3. So this yellow line is my vector 2, 3. And I apply a transform, and it actually shifts it off the page. Let's bring this down to 2, 1. Still shifts it quite far off the page. There we go. Let's apply half a transform. And that moves it to 1, 3. And we can do this, so I'm hiding the what is actually causing this transformation for the minute, but I can change what the transform is quite quickly. But it's just a case of mapping it from one thing to another, and it's a smooth translation, okay? This, like, scale factor, call it for now, in the transformation that I'm playing with. As I slowly increase that number, it slowly and smoothly changes where my vector is, the value of my vector. And importantly, what it's doing is changing the values of I and j as well, or it's mapping I and j to some new basis vectors I and j, and it does that for any vector in the plane. So I can also do, I think if I do it here, there we go. So I can put some more vectors in, 0, -5. So I can plot some more vectors, and then I can look at how they all change. And we can see that this transformation is doing like a rotate and a stretch and applying to it, but it's moving all of them the same way. And this is an example of a linear transform. So I think I can just set that playing and it'll just keep bouncing back and forth. There we go. We'll just leave that going for a minute. Thank you for the follow. Welcome in. So what's important to notice with this is, like, the reason that this is called linear transform is that you can see that even though it's mapping the entire area, there are two factors about it. One is that the origin, that center point, is not moving, and the other one that it's mapping sort of straight lines to straight lines, and it's evenly distributed. So where things were sort of equidistant apart, the original grid with no transform applied is uniform grid. This is a shifted and stretched uniform grid, but parallel lines are parallel. So all of the lines that were the y-axis are all pointing in the same direction, and all the lines that were the x-axis are all pointing in the same direction. And this is just an example of one. I can do a different grid and shift things in a different way. And it will do the same thing of everything sort of gets stretched and scaled in about the same factor. A non-linear transformation would do things that lose these properties. So instead of mapping straight lines to straight lines, it might map straight lines to circles, for example, and then you sort of lose some of the underlying characteristics. Now we're going to define that mathematically now. And what I'll do is, with the VOD, I will definitely post the link to this Desmos underneath. Credit to the person at the top that made it. I did not make this. I wish I made this. I did not have time or capacity to do it. But there's a lot of things that you can play with, and the spoilers down the bottom are things that we're going to look at throughout the rest of this this linear algebra series. So this is probably going to be a tool that we use quite a lot. So let's come back over here. My maths teacher used to get so excited showing this. It's really fun. It's one of those things as well, like an obvious shout out to 3 Blue 1 Brown, because they have a fantastic video series on it. On like intro to linear algebra stuff, through very similar avenues to what we're doing. I'm just trying to be a bit more like mathematical lecture notey about it. So, where are we here? So let's do some definitions. Is the series publicly available? So this is exclusively for Twitch. These are designed for Twitch. These are designed for these live streams. They will be included on YouTube, publicly available, because I, as much as I possibly can, don't want to put anything behind a paywall. But I am writing lecture notes specifically designed for this platform. Hi. Or the other platform that they will be on down the line. If you're watching this on YouTube, hi. Thank you for watching. But yeah, it's here, it's what you've wanted. We actually had a vote in the Discord about what lecture series to do. And yeah, it's community driven, which is really fun. I like it. Okay, so definition. A transform L is linear if for vectors u and v and scalar k, it satisfies two rules. And that is that we can take a linear transform of a product of a sum of vectors, and it's the same as doing a linear transform, or it's the same as the sum of the transforms of the vectors. Yeah, so the transform of the sum is the same as the sum of the transforms. And any scaling, oh wait, no, wrong way around. The transform of a scaled vector is the same as the scaling of the transform vector. And this is the one that sort of sets that origin equals 0. Okay, because anything that we times by our 0 vector, which maps to the origin, is the 0 vector, which maps to the origin. So any linear map that we apply maps to the origin. And that's where you might have seen transforms in school as like rotations, reflections, scale factors, and translations. Rotations, reflections, and scalings are all linear transforms. Translations aren't. So translation being when you sort of shift everything to the right or shift everything to a new place, and the whole thing sort of space preserves, orientation preserves, but just moves. No longer a linear transform, because you lose that like origin to origin-ness. The first rule also forces L of 0 is 0. Oh yeah. Yeah, so depending on which rule you go to, so since like k0 equals the 0 vector, but also v plus the 0 vector is just v. So both of those rules for matrix algebra, vector algebra set mean that the linear transform doesn't move the origin. Good spot. Okay. How on earth does this connect to matrices? We will find out after a short break. So I will see everyone in 5 minutes. I'm going to go stretch. I recommend, we've been going for just over an hour. I do recommend going and having some water or some food, or stretch and move around if you need to. We will be back shortly. Okay? I will see everyone soon. Hello. Oop, hello. There we go. Okay, let's get back into it. Here we are. So we left things off with definitions of linear transforms, being those that we can apply the transform to a product of vectors, and it's the same as we can apply a transform to a sum of vectors, and it's the same as the sum of the transforms of the vectors. And the transform of a scaled vector is the scaling of the transformed vector. So both of those things help us fix our origin at the same point and essentially say sort of straight lines go to straight lines. Our addition and scale factors should basically behave the same once we apply those transforms. And I have lost myself in notes. There we go. So how do we connect these back to matrices? Well, let us just gonna move y'all down slightly. There we go. Let's take a vector v as v1 and v2. And I'm doing all of this in sort of R2 space, like 2D space, mostly out of ease of writing rather than out of we can't possibly do it in anything else. For now, assume that it's pretty standard. It's just easier for us to do it in this way. So we take our vector and apply a linear transform L to obtain a... Oh god. I do not know what happened there. Let's pretend that didn't happen. Okay. Remember that we can write V as the coefficient of the first element of V times I plus V2J, where I is 1, 0 and J is 0, 1. And if we were in 3D, it would be plus V3K, where K is 0, 0, 1, okay? And V1, V2 are scalars, which were our elements of our vector. Then we have that the transform of this vector V is the same as saying the transform of V1 times I plus V2 times J. Now V1I and V2J are themselves vectors. And because it's a linear transform, we can separate this out. So we can do the linear transform of V1I, add the linear transform of V2J, okay? And that's from that first rule up here. And then we can actually do something with the second rule as well, where here we have, it's a coefficient, a scalar coefficient times a vector, and we can take that outside of the transform as well, and that gives us that V1 L of I add V2 L of J. Now what that means is for any vector, we can apply the linear transform to the vector V by multiplying the elements of V by the linear transforms of the basis vectors, okay? So in order to determine what L is, we just need to look at how it changes I and J. And now I and J are really nice vectors to play with because they are always 1, 0 and 0, 1, whereas V might be like minus 73, 62, and doing complicated maths with that is more complicated, and we don't want to do that. So I claim, I actually have loads of space. That applying a linear transform is exactly the same as multiplying by a vector. And what I mean by that is we can apply any linear transform, or applying a linear transform is the same as multiplying by a matrix A for a specific transform and a specific corresponding matrix. So let's see what that does for a second. And I do like, this is the closest that I get to doing proofs. So keep that in mind, that this is Cat attempting to be rigorous with the maths. If we let the linear transform of I be the resulting vector AC, and we let the linear transform of J be some vector BD, okay? So whatever this transform is for a specific vector, for a specific linear transform, it takes 0, 1 to the coordinates AC, and it takes 1, 0, no, other way around. It takes 1, 0 to AC, and it takes 0, 1 to BD, i.e. 1, 0 gets mapped to AC, and 0, 1 gets mapped to BD, okay? Applying this map does this rotation. then I claim that L of V in this instant is the same as multiplying by AV, where A is the matrix A, B, C, D. And I'll show you how that is true in a second. But that is sort of my proof, or that's my statement, is that this is what that is. So the linear transform that maps I and J to these column vectors is the matrix whose columns are the new mappings of I and J. I'm going to try and write that out in words. I don't know how to write that out in words. I did just say it. That's close enough. But essentially, yeah. So the columns of the matrix that is the linear transform is what I and J get mapped to. So if I want to do this sort of rigorously, I would say AV is, so remember, A, B, C, D. Make my... and V is V1, V2, remember. Then doing my matrix multiplication, remember that it's the same number of rows as columns. So you take the first entry is the first row of the first matrix times the first column of the second matrix. So that's AV1 plus BV2. And there's no more columns, so we're all right. I'll close that off. And then the second row is the second row of the first matrix multiplied the first column of the second matrix. CV1 plus DV2. Okay. Now, this is the same as I can sort of pull these out. So we're the adding of vectors here, so that they have a common factor v1 and v2. So I can say that this is AV1, CV1, CV1, add BV2, DV2, because when we add vectors together, we add element-wise. So we add the top and we add the bottom. So I can just pull that out, and then I can pull out my coefficients. This is V1 times AC. Add V2 times BD, because element multiplication. Let's pull out both common factors. But I told you that AC was the transform of I, and BD was the transform of J. So this is the same as V1 L of I plus V2 L of J. And then I'm going to sort of work backwards. So I'm going to actually put the V's back in, which is the same as the linear transform of V1 of I and the linear transform of V2 of J. And then I can add my linear transforms together. So this is the same as the linear transform of V1 of I, add V2 of J, which is the linear transform of V. Ta-da! So for an arbitrary vector V, if this column maps the new I and this column maps the new J of a matrix A, it is the linear transform of that vector. I think that's the closest we're getting to a proof for today at the very least. So let's do an example of this, and then we're going to go back into Desmos and see if I get my answers right. Okay, so I'm going to take the matrix A as 4, 1, 0, 2, and I'm going to take my vector V as 3, 5. So I have claimed that I can just read out the columns here 4, 0. I really want to use round brackets. 1, 2. And we can do it both ways. Okay, so let's do A times V first. So that's 4, 1, 0, 2 times by 3, 5. So we times across and down. So first entry, so 4 times 3, add 1 times 5. And then we do the same on the bottom. So 0 times 3, add 2 times 5. So that gets us 12, add 5. So that's 17 and 10. So I claim that the linear transform of V is going to be 1710 for this matrix A. And we can do it the other way as well. So I also claimed that we could do V1 L of I plus V2 L of J, which would be 3, 4, 0. And you'll see that actually the maths that I'm doing is basically the same. And this is where sort of multiplying across and down will give you roughly the same thing. So that gives me the vector 12, 0, add 5, 10. And then adding those vectors, we add element-wise, so we get 17, 10. So both ways of doing it, we get 17, 10. Now, if matrix multiplication like this scares you, this way is a bit more like step and bringing it out, which is quite nice. So let's shift over to Desmos. Okay, so I have my vector 3, 5. I've got a feeling this is going to go completely off the grid. And what I have here, so when we're doing these transforms, this is the matrix. So ij, and I've got 4, 1, 0, and 2. And the vector is 3, 5. Then what we should get as we rotate this is it flies off the page. Fantastic. And that maps to 15, 10. Interesting. Okay, well, we can check our work anyway by checking that our basis vectors have mapped to the right thing. So this is why I left the squares in the old grid in the background. That's what you can see. So we can check that I should map to 4, 0. So we go across 1, 2, 3, 4, and that's our new I value. I can zoom in to check that. And J goes across as well. So make everything a bit bolder, should be nicer to see. So J goes to 1, 2. So go across 1 and up 2. So at the very least, that has worked. I will figure out where I've gone wrong later. Oops. But yeah, so that's how we can do our transforms, is either by just taking the vector as is, or doing this ij and then multiplying by the coefficients, which is slightly nicer. And you can think of it in the same way. So if this new grid point 15, 10, yeah, okay, it's definitely messed up because it's, there we go, 17, 10. I think the plotting function sort of runs out a bit after a certain amount. But we can do something with a slightly smaller vector. Let's go for 1, 1, and zoom in. So in the old grid, it goes across 1 in this I direction and up 1 in the J direction. And if we scale it, we can see that it goes across one amount of I in this new grid system and one amount of j in this new j system. So even though our sort of grid has shifted, the ratios are unchanged. And that's where that linear transform is. So I can do half a transformation, and it gives me the same thing. This vector here is still one amount of I and one amount of j. We've just changed what I and j are. And that is going to be something that pops up a lot later down the line. And also in more broad sense when we start looking at things like calculus and transformations of change of bases and all this sort of stuff. But I think that's pretty neat. I think that's a nice way to think about it. So it's just we're shifting and stretching and scaling sort of our entire plane. And again, look that the origin sort of stays unfixed. It's I and j that shift and scale, but it doesn't actually change anything. And I think this one's a really nice one as well, because if we actually look at our x-axis, it's not actually rotating at all. It's everything on the x-axis before is staying there. And that's because this 0 value here, nothing is being moved in the y direction. If I were to change this to a 1, we can see that a 1 transform is now gone up 1, whereas before it stayed on there. And this is where if I do the same thing with the j and I change that to 0, then the transform here is just stretching and scaling along the axes, but everything stays horizontal and vertical as we're used to them. It's these opposite diagonals that start introducing any sort of like stretching or rotating that we start seeing, whereas here we're just scaling. Now the other one that we want to look at is, well, okay, so if that's a stretch, and we remember when we multiplied through vectors by scalar values, we had sort of anything bigger than 1 stretched it, anything smaller than 1 but bigger than 0, still positive, squished it, anything negative, flipped it. What happens if the values are just 1 and 1? And the answer is nothing, okay? We multiply by 1, we don't change the value, it stays the same. I'm going to leave this on full transformation just so we can see. If I change this to 0.5, we can see that everything has shrunk by a half in the x direction. If I also change this to 0.5, everything shrunk in the y direction. If I change this to 2, it stretches. Change this to 2, it stretches in the x direction. Let's put it back to normal. And then if I introduce negatives, I flip things. So here we've kind of gone through and rotated and reflected. And again, -1 minus, not 11, -1, flipped it that way. So we have sort of a reflection in this direction. So let's come back and write down sort of what this all means. So the transform L with matrix 1, 0, 0, 1 is actually the identity. So if we remember when we were talking about multiplication or addition, there was the identity was the mapping something to itself. Transform which maps everything to itself. So L of V is just V, and this is V times I times V, where this is our 1, 0, 0, 1, which is the identity matrix. And I've written I instead of A because it's all, the identity is I. We denote it with I. So I is always M by M. it's always square, and its entries are 1 if I equals j, and 0 for I not equals j. I'm going to use A because I don't want to do ij. That's confusing. But its values are basically 1 along the diagonal, 0 everywhere else. Okay. Other classic transforms then. Actually, I want to go back to Desmos and do these. Okay, so identity matrix was 1, 1, 0, 0. We have reflection in the x-axis is just swapping everything around, so minus 1, 0, 0, 1. Reflection in the y-axis then was minus 1 is 1, 0, 0, 1. Also, when I'm reading these, I'm doing left to right, then top to bottom when you read out the entries in a matrix. But it's this matrix here. Ah, we can set little dots. That's fun. I'm gonna make this like just to make it a bit clearer to see. So yeah, setting one of the entries along the diagonal to negative, we'll set them to negative. We'll flip it in this direction. Ugh. Doing both is the same as flipping in the x and flipping in the y, or reflecting along y equals minus x. We can have scaling by multiplying the same values on both sides. So let's call this 2, 2 is just scaling in all directions the same, or scaling along the x and y the same. And this would be the same as writing coefficient times by the identity matrix. Remember that multiplying a scalar goes in the same way. Then we have the other thing we were looking at was sort of more funky things, right? So here we have sort of a nice stretch and rotate. Like if we look at this transformation, right, it looks like it's rotating. And what's actually happening is it's sort of stretching in the one direction and stretching in the other, and that's giving it this twist. And what about if we didn't want to scale it up? What if we didn't want to stretch it, we just wanted to rotate? Well, we have to do something a little bit complicated. So p equals pi for a second. And this is where using sine functions come in handy. Cos of p minus sine of p. This is one of those matrices that like does come in handy and makes sense when you also think about what we were just doing with the ones and zeros because of the value of cos and sine being at maximum 1. But if I do this, what you get is a cool shrink, and then everything pops out the other side. And when this value is equal to pi, it's the same as rotating by pi, or rotating by 180. If I pull it back, and instead I do pi over 2, then as I apply this transform slowly, what we get is a shrink, but an expand, and it's just a rotation by pi over 2. So everything is shifted 90 degrees. And now what I think is really cool is that I has gone to where j was, j has gone to minus I. We can do the same thing again. And if we do 3 pi over 2, rather than rotating clockwise, it's going to still rotate anti-clockwise. It's not. It's going to rotate clockwise now. And it goes that way. That's interesting. Interesting. So it's not a smooth transform, but we can scale the values of p. If I knew how Desmos worked. Oh yeah, 0 less than p less than 2 pi. All right, set that to 1. And set that, and then you get a rotation. Isn't that cool? So by shifting the angle, so P here is the angle that the thing is shifted by, so we can rotate through. And if I instead change this to 2 pi, we should get even faster, and it will just rotate through. Which is quite funky, I think, at the very least. And we can actually keep going, so these transforms aren't unique. This 2 pi is the same as going to 4 pi, and we're going to slow it down by a half just so it doesn't speed up, because it will keep going otherwise. But this is the same as rotating again, and then it'll bounce and go back the other way. And that's just because of the periodicity of sine and cos functions there. But those are some like classic transforms. So other ones are reflection in the x direction is the matrix -1, 0, 0, 1. Reflection in the y direction is the same, but with now 1, 0, 0, -1. And thinking about these matrices as their columns being where I and j get mapped to is really useful. Scaling by some number k. A is k, 0, k, 0, which is just k times I. And then finally, rotation about theta, anti-clockwise, is the matrix cos theta minus sine theta, cos theta. And there's some really cool trig behind the scenes going on there. And what these map to, if V is V1, V2, and V through all of these matrices map to AV is sort of V prime again. Here, V prime is minus V1, V2. Here, V prime is V1 minus V2. Here, V prime is going to be KV1, KV2. And the final one, which I'm probably going to need to, let's do it down here. The rotation one is V1 cos theta minus V2 sine theta, V1 sine theta plus V2 cos theta. Ta-da! One final really cool thing, or I think really cool thing to end on. You can perform any rotation via a series, and I think 2 of reflections. So through some combination of reflections and scalings. You don't actually have to do that rotation thing. You can bounce through it. And think of your rotation as from pi, so flipping everything is the same as reflecting in the y-axis. And that's just because of this linear combination behavior that we get from transforms. So that is actually where I'm going to leave it today. So just covering everything again. We had a really brief recap of vectors, and in particular really started thinking about vectors as these coefficients multiplied by our basis vectors, our I and j. And these are our sort of unit vectors in our coordinate system that we're working in. In Cartesian, it's along our x and y axis. We introduce matrices as an array of numbers, and we introduce Einstein notation. We introduce the fact that when we write matrices, we write capital letters, and an m by n matrix is m rows and n columns, and each entry, each element is the ijth element, where diagonals are a11, a1, a22, and so on, until amn. Matrices don't have to be square being where they are the same number of rows as columns. They don't have to be, but they can be. Series of examples. When either the number of rows or the number of columns is 1, it is a vector, or that is a column vector, a row vector, and our vector algebra starts to apply. If both m and n are 1, it's technically a scalar, because it's just a number. And if we really wanted to start thinking about it, we can think of the space of scalar numbers as a subset of a space of vectors, as a subset of a space of matrices, as a subset. And then we talked briefly about the fact that tensors are like the biggest version of this, but don't worry about that for now. I kind of said we're going to stick to around nm equals 3 is the biggest, because I don't want to write out more than that. And we introduced some algebra. So we did matrix addition. We just add element-wise, nice and easy. We introduced the transpose operator. That's where we just flip it along its diagonal. And this is where row vectors become column vectors if we were to flip along that diagonal, which in a vector is just its first entry. Don't know why I said it as entry. Sorry, just brain pause about why it's called ents. Anyway, then we did scalar matrix multiplication. We just apply the matrix, so we multiply that matrix by every element in. We multiply that scalar by every element in the matrix, and that's how we do scalar multiplication. Then we did matrix multiplication, and that requires the number of columns of the first matrix to be the same as the number of rows on the second matrix. And basically for an m by k times by a k by n, we get an m by n, and we get rid of that k. And we introduced the Einstein notation, and then we did an example where I tried to color match all of the entries. When we went back to linear transforms, so remembering our definition of our vector as coefficients v1, v2 multiplied by I and j, where I and j are our unit vectors in each direction. We think about transforms as sort of like smoothly mapping a vector to a new vector. And we do maps by these nice curved arrows, and we describe the maps as like these functions, L, and I did a nice curly L for that. And then we introduced some Desmos, and we did a really cool look at what that looks like. And we highlighted the fact that the transforms that we were looking at, small changes in the values of whatever the secret transform I was doing is, resulted in small changes to the vector. And we looked at what it meant for a vector, for a transform to be linear. So mathematically, it's linear if the transform of the sum of vectors is the same as the sum of the transform of the vectors, and the transform of a scaled vector is the same as the scaled transform of the vector. And both of those mean that the origin doesn't move, and sort of straight lines stay straight lines. Vectors directions don't shift once we scale them with in and without transforms, and the sum of vectors is the same, which is pretty cool. I then showed you what that meant mathematically. So doing that with thinking of vectors in this IJ notation, we can say that it's the same as multiplying by a matrix. God damn it, we nearly made it without any more mistakes. Multiplying by a matrix. Specifically, the matrix corresponding to the vector has columns that are where you map I and j to. And I proved it in blue. So matrix multiplication, A times the vector v. I swear this is just like going through and checking my homework. Is the same as applying that linear transform, if the linear transform was to map I to AC and J to BD. Did an example, managed to not mess it up too much, and then introduced some classic matrices and transforms. So the identity matrix has main diagonals 1s, 0s everywhere else. 5 by 5, for example, is 1, 1, 1, 1, 1 all along the diagonals, and 0s everywhere else. And then we did some classic transforms. So because we can think of our columns of our matrix as where I and j map to, it's quite nice to find reflections. You just take the negative values and you flip it. Scalings, again, apply through to the entire diagonal, and that's the same as doing the scaling times the identity matrix. Rotations are a bit more complicated, but I left you with a little aside of any rotation matrix can be written as the series of reflections or scalings. And you should be able to get to the same thing. And that's basically where we've covered up to today. So, yeah, let's leave it there. Ta-da!